So today we have Tim Stumpf-Fetizon telling us about exact Bayesian inference for Markov switching diffusions. So huge thanks for Tim to giving the talk today. So he helped us out to find to fill this slot. So if anything is wrong with his talk, also blame me, not just him. So please go on.
Yeah, and again, I'd like everybody to just jump in and interject whenever they feel like it. That'll make it feel a bit more social. Yeah, thanks to Yure, Masi, and Alice actually for the invitation. So yeah, as Yure said, I'll be talking about exact Bayesian inference for Markov switching diffusions today, and actually for diffusion models more generally. And this is joint work with my supervisors, well, Chris and Gareth at work, and Jan Polczewski. So the structure of the presentation is that first, well, I'll be saying a few things about what the kind of model looks like that we're interested in, then go on to what the inference strategy is, and then I'll start building a pretty tall tower of methods that we need to make everything work. And actually, lucky for me, the Dutek had a presentation on some of those methods. Not long ago. I think that was 2 weeks ago. So that might. Sorry, am I still connected? I'm hearing.
Yeah, no, the problem. It's not your fault.
No,
yeah,
just,
okay.
just ignore the sound.
Yeah, and then I'll talk about how to customize those methods to work robustly in this specific context. And finally, I'll show you some output on a simple application. So what is a Markov switching diffusion model? This is a trajectory that was generated from one such model. And the trajectory is colored by the regime that the Markov switching model is in. That is, the idea is that you have an underlying discrete state continuous time Markov process. And depending on the state of that process, you have a diffusion that changes its behavior. So as you can see here, I think it's quite apparent that in the orange state, the diffusion model likes to stay around a mean of 3 to 4, and in the blue state, it wants to go towards 0. And well, this is simulated data, but actually, if you were to look at say an interest rate time series, you might get rather similar behavior. So mathematically speaking, what is this regime process that I'm speaking of? So above, I'm giving you just what the corresponding trajectory to the previous figure of the hidden Markov model would look like. And in 2 states, it's actually a pretty simple description. That is, starting from some state at time called 0, you switch to the other state after an exponentially distributed time. And so the rate of that exponential depends on the state that you're currently in. And then you just iterate that on, and that gives you a 2-state Markov jump process. And so more generally, you'll have in more than 2 states, you'll have a bunch of those transition rates, where lambda ij then is the transition rate from state I to j. You put all of those together in a matrix, and that's called the generator of that process. But in this talk, I'll just stick to the simple 2-state setting. And then on top of that regime process, we have a so-called diffusion process. And so those of you that aren't familiar with continuous time diffusion processes and SDEs, you can sort of think of this as well, very informally speaking, as starting with some process in discrete time, where the increments you obtain by having some drift that is a function of the current state, and then some volatility that is also a function of the current state, multiplying an increment of a Brownian motion. And under appropriate regularity conditions that I'm not going to torture you with, there is a limiting process if we take the time increment to 0. And so that process then is commonly described in the form of an SDE, which is equation 2 here. And yeah, that's just an infinitesimal version of equation 1. And so in that description, the process characterized by an instantaneous drift function mu and an instantaneous volatility function sigma. And in what follows, I'm going to parameterize those in terms of vector theta. And so what distinguishes this model from an ordinary diffusion model is that now the instantaneous drift and the instantaneous volatility can change with the regime process. So they can go through discrete breaks. And as in the ordinary diffusion case, the transition density, that is the density of an observation in the future given the current observation, is not available. So this is a classical intractable likelihood problem. And yeah, this is really the main complication of this setting, and why this is even worth talking about. And so if we now move into the statistical realm and pose a statistical problem of inference for theta, which is the parameters of the instantaneous drift and volatility function, inference for the hidden Markov model, which we usually don't observe, and the generator thereof, just given a set of discrete observations. So in that figure, you can think of the black dot being what you're given, what we see, and given that, we want to find everything else. And so we're gonna be in the Bayesian paradigm here. And we want to sample from the posterior of the diffusion parameters, the hidden Markov model, and the generator, given those observations of the diffusion that we see. Now, how are we going to go about doing this? We want to carry out Bayesian inference, and for that, in principle, we need access to the transition density and to compute the joint probability of everything. And what we want to achieve here is to, in spite of not being able to target that transition density, we want to build an MCMC algorithm that targets the exact posterior, and exact in this specific sense I would explain by having unbiased estimates with respect to the true posterior, and we want the Markov chain central limit theorem to apply to the estimates that we get from that MCMC algorithm. And in particular, that means that standard errors are bounded above by, well, the standard error is bounded above by the inverse square root of our computational budget. And this does not apply to common discretization methods. So actually, if you remember how I motivated the SDE, you can go the opposite way. You can say that we're going to approximate equation 2 by equation 1, which is tractable, and then use that to carry out inference. But that doesn't give us our first item. This is going to give us biased estimates, and the MSE is going to recede slower than O of the inverse square root of the computational budget. We also want an algorithm that is in principle model agnostic, meaning you could plug in any mu and sigma that fulfill the set of assumptions, and the algorithm takes care of the rest. And finally, we'd like to avoid something that only makes sense if you put it on a supercomputer and run for a month. So in particular, the output that I'm going to show you, that is the result of running it for 1 day on a single core on my home computer. The high-level strategy to achieve those goals, essentially consists of 4 steps. In the first step, we want to take that diffusion process V and transform it to another process with a tractable dominating measure. I'll explain what exactly I mean by that in the next slide. Then we just follow the standard strategy of augmenting with missing data, and do it in such a way that conditional updates of a subset of the state space of the algorithm are easy. So we don't want to do more of it than strictly necessary, since that tends to slow down and then into the algorithm. And so in the next step, once we've done the right kind of augmentation, we'll have an infinite dimensional gift sampler. In particular, the updates are going to be the parameters of the diffusion, given the missing data, and vice versa. And then finally, we need to find a way of carrying out these updates based only on finite information. And the area we're going to leverage Barker's algorithm in conjunction with Bernoulli factories and the exact algorithms for diffusion simulation. And again, I hope that you attended Didiger's talk 2 weeks ago, because that's going to make my job much easier. Now, I'm going to have to introduce a little bit of notation. Hopefully, this is not more than strictly necessary. In particular, so think about having observations, 2 observations at time 0 and time s, and having jump times of the hidden Markov model in between. So in this illustration, tau1 is the jump time of the hidden Markov model in between the 2 observations. And observation times and jump times in conjunction, I'm going to call tau. For simplicity of notation, and because we haven't quite figured all the quirks of the more general case, I'm going to assume that the instantaneous volatility does not depend on y. And also, I'll just stick to a simple 2 observation setting. Again, this is without loss of generality, where we observe the diffusion at time 0 now. And I'm going to use the notation. I don't think I can mark in full screen. Hope you can see my cursor. Tau dot twiddle tau dot dot to denote 2 consecutive jump times in the set tau. Ancillary quantities that aren't really relevant to the presentation, I'm just going to gray out. And I'm not going to talk about inference for the generated lambda of the regime process, since that is conditionally conjugate for appropriate power, so not very interesting. Any questions about this notation? Please jump in right now. All right, I'll just keep going then. What is the right kind of missing data augmentation here? Really, the idea is to leverage the Markov property of v and y. And to do that, the best thing to do is to augment with the value of the diffusion v at all times tau. So in terms of the previous illustration, that corresponds to augmenting with the value of the diffusion at time v tau 1. And then the transition density of the diffusion at times tau, given some starting value and assuming that we know the regime process, is just the product of the laws of an ordinary diffusion, because y is constant between times tau dot and tau double dot. So if we do that augmentation, we can then move on and apply tools from, already fairly well developed tools from ordinary diffusion inference. Now, back to the idea of transforming V to a process with a tractable dominating measure. What we're going to do is to transform it such that the process X has constant volatility, or volatility, instantaneous volatility 1 in that case, where we define the Lamperti transform, as an equation for the antiderivative of the inverse instant volatility, and then the reduced process X is what you obtain if you put V through that transformation. And that process has an induced measure, and the following SDE, so delta is implied implicitly, is defined implicitly, and again, it has unit volatility throughout. And then by the Gasana theorem, and again, under appropriate regularity conditions, essentially integrability conditions on delta, we get a density of that process with respect to the linear measure, which takes the form in equation 6. And so of particular interest here is the exponential of that path integral, which we write in terms of this function phi, which is itself, which derives itself from the jar. So yeah, this is a density of sorts for the path of the process X between times tau dot and tau double dot. And if we just change the dominating measure to, the Lebesgue measure for the endpoint and the Brownian bridge measure between values x tau 1, x tau dot, and x tau double dot, we obtain, you could call an augmented transition density for this section of the path of X. And if we then switch the section of X to a non-centered parameterization, essentially by just removing the points, such that Z under that transformation is a standard Brownian bridge, then finally we get a density for the non-centered section of the path and the observation D tau double dot in terms of that original Rana-Nikodym derivative. So now we actually have something that is, we have a density in something that is infinite dimensional, but that could be in principle tractable. And if we put those bits together between any two observation times, we actually get the augmented transition density of Vs given V0, adding the path in between in a certain parameterization. And H then is going to be the full missing data augmentation set. And once we have that, we can, in principle, define an ergodic Gibbs sampler that has one update where we refresh the missing data, and another where we refresh the parameters given the missing data. Now, the second one is of particular interest because it also applies to ordinary diffusion inference. And also, in a sense, it's harder to carry out. So I'll be focusing on that in this presentation. Now, I went through quite a few things, the details of which aren't necessarily critical, but still it might be a good point to jump in and ask me to go into some more details on some parts of it. All right, I'll just hope that this means that I was reasonably clear. But if you remember, in our definition of these densities, pi of h and ds given everything else, we have these path integrals over a rough path x. So these we can't evaluate exactly in finite time. And so there are multiple approaches to addressing that, which is, for example, use the pseudo-marginal method, where we would apply some unbiased estimator of the exponentiated path integral. So the exponent really is the main problem here. You could easily have an unbiased estimator just over the path integral, but estimating the exponential path integral is harder. You could do even more augmentation, which is, well, unattractive because it tends to slow down your algorithm. So what we're going to do here is combine Barker's algorithm with Bernoulli factories. And this is going to keep the state space of the algorithm as it is. That is the state space consisting of the missing parts of the diffusion, the hidden Markov models, and the parameters of the diffusion and the hidden Markov model. Yeah, for that, I'm going to have to pull in a couple of methods. And they sort of rely on each other. It's a bit like a tower of methods where we are going to be working our way up. And so the first level here is Barker's algorithm. So Barker's algorithm is like a lesser known cousin of the Metropolis algorithm, which I imagine everybody here has heard of. If you think of a target density, pi of a, and proposing some update to that density, to a, which I'm going to call a dagger, according to some proposal distribution, then the Metropolis-Hastings algorithm accepts with the probability in equation 15. But really, that's not the only thing that then gives you a Markov chain with stationary density corresponding to pi of a. For example, Barker's algorithm accepts with, well, a different acceptance probability given in equation 16. And so that is not as popular because it results in a higher asymptotic variance for a given proposal. So why would we bother applying this? This is where the so-called two-coin algorithm comes in. Suppose we can generate coins with probabilities P1 and P2. Then the two-coin algorithm is a device that gives us a coin corresponding to the probability in equation 17. And so that already looks fairly similar to Barker's algorithm, doesn't it? And so this makes the two-coin algorithm an example of a Bernoulli factory. And above in figure 6, there is a probability flow diagram that shows you how the two-coin algorithm operates. So you start out with flipping a coin that has probability of heads C1 over C1 plus C2. So here we assume that these quantities C1 and C2 we can evaluate, and tails with probability C2 over C1 plus C2. And then assuming, for example, that I flip heads, I go on to coin C1, and I return 1 if that coin comes up heads with probability 1. I return C0 with probability 1 minus P1. And here actually you can already see what might go wrong in this algorithm, which is that if probabilities P1 and P2 are both quite small, then you can go on circling for ages. So yeah, the runtime of that algorithm, the expected runtime as a function of P1 and P2 diverges to infinity as P1 and P2 become, well, close to 0. And so if we assume that there exists a lower and an upper bound on phi, so that was the integrand within our path integral, then we can write the acceptance odds in Barker's, well, in terms of Barker's algorithm for some parameter proposal, as I do here. So this is for the update of the parameters of the diffusion given the missing data. And this then gives us an expression in terms of, again, ancillary constants C for both the proposal and the state that we can evaluate exactly. And it gives us these intractable probabilities in the numerator and the denominator of the odds. And since we assumed that we had a lower bound, we can just shift the path integrand to make sure that this is actually a probability. And so if we could simulate from coins with probabilities corresponding to what's in the numerator and the denominator, then applying the two-coin algorithm, we'd have a way of just simulating a coin with a probability corresponding to the acceptance probability in Barker's algorithm without ever computing that probability. So really, usually that's what we do. We compute the probability and then we of acceptance and then we flip a coin. But strictly speaking, we're only really interested in the outcome of that coin itself. So here we bypass the evaluation of the probability of that coin and just go straight to the outcome. So how do we go about that? That is actually the final level in our methodological tower. So how do we go about flipping these coins? Think of having a path integrand f, which is lower bounded at 0 for simplicity and has some upper bound on some time interval. And if we simulate a unit intensity Poisson process on the rectangle, which corresponds to the time interval and the line segment between 0 and the upper bound, then the probability that all points in that simulated Poisson process are above the graph of f is this exponential of the negative path integral. And this is called the Poisson coin algorithm, and it's applied, for example, in the exact algorithms for diffusion simulation. Now, assuming that phi has indeed that lower and upper bound, you can just go ahead and apply this Poisson coin algorithm to simulating coins with the right probability. This is just substituting f for the actual integrand that we're interested in our specific setting. So in the illustration above, this just shows you an example trajectory of the path integrand, and all points in the Poisson process that fall into the green space are, well, if all the points in the Poisson process fall into the green part, then we accept. If any of those points fall into the red part, we reject. Now, this in principle would give you an algorithm that you can implement. The main remaining, but there are some remaining issues in actually making this practical in terms of this problem with the runtime of the two-coin algorithm that I mentioned before. So regardless of what our parameter update looks like, how close theta dagger is to theta, standard conditions as your time horizon recedes. So actually, I've got the wrong limits on the integral here. Think of the lower limit being 0 and the upper limit being f. And if you increase f, then this probability is going to go to 0. And this applies both for theta and theta dagger. So as you increase f, the two-coin algorithm is going to slow down further and further. And well, increasing f corresponds to, for example, tacking on more observations onto the end of your time series. And you run into those constraints very quickly. For example, that if you think of that example time series here, if we were to try to implement an algorithm based on that description I gave you, you would be computing for years without finding a satisfactory answer. Where was I? But actually, what saves us here is that there are various two-coin algorithms that result in the same coin probability. And we can see that by just arranging terms in the acceptance odds, so the odds for the parameter step. And well, after doing that, we end up with the right-hand side in equation 24, which is an entirely different path integrand, but we still have the exact same acceptance odds. And it's worth looking at the path integrand a bit more carefully. So this is just the difference of the two path integrands for theta dagger and theta. And by the mean value theorem and Cauchy-Schwarz inequality, this is bounded above by the total derivative of the integrand, well, bounded on some convex hull, including the parameter proposed in the parameter state, multiplied by the this is the L1 norm of theta dagger minus theta. And so if we make the step small enough, we can push the integrand down towards 0. And pushing down the integrand towards 0 everywhere then increases these probabilities in the numerator and the denominator. So again, in the numerator, the exponential, and in the denominator, the exponential, those are probabilities. And we can make those larger by making the parameter steps smaller. Now, to make that practical, we actually have to find an upper bound on, this should actually be the absolute value of that total derivative. And this is a very complicated expression, even for quite simple models. And to make this, well, both practical and model agnostic, what we do is use symbolic algebra to just work it all out, bound it, and then give us some code that returns evaluations of this expression. Now, how does this fare in application? Again, this shows you as the black dots the observations that we see, and behind you have the ground truth of the diffusion path. And this was simulated from a so-called generalized CIR model, which which can be expressed as the SDE in equation 29. And that is, it's like a compromise between the standard Cox-Ingerson-Ross process, which has an exponent 1/2 in the instantaneous volatility, and the geometric Brownian motion, which has exponent 1. And this is a stationary process for, a given state of y, which will revert towards mu. And the speed of that reversion is controlled by beta. So for a very large beta, you will tend to revert towards mu very quickly, and vice versa. And so for values of the exponent in the instantaneous volatility between 1/2 and 1, so that's on the interior of the interval 1/2, 1, you stay away from 0 almost surely. So that makes it an appropriate model for interest rates, well, traditionally, since interest rates tend to stay above 0. And we're going to use the prior on the parameters of the diffusion corresponding to independent log normals for all the individual parameters. So there is one mean reversion parameter for each state of y and one stationary mean parameter. And so the posterior here is actually invariant label inversions. That's something that you see, for example, in mixing models or ordinary hidden Markov models. That is, if we change all the labels of the regime process that are 1 to 0 and vice versa, you get the same, and you invert, you invert the parameter vector, where the parameters that were corresponding to state 0 are now for state 1. Then you get the same posterior density. And so the posterior for beta 1 and for mu 1 are really the same. And for beta 1 and beta 2, and for mu 1 and mu 2. And if we look at what actually happened in the run of that algorithm, then we see that, within a day's runtime, we actually haven't quite reached that stage. So on the top, for example, you have the trace plot of the mean reversion parameters for each of the states, and the quantile estimates don't entirely overlap. So we'd have to run this for a little longer to actually recover that invariance that we know theoretically must hold. And the same applies for the stationary mean. So, this is an issue though that would really apply to any algorithm for this model that augments with the hidden Markov model Y. And one informative summary is also to plot the density of the jump times in Y. And here I've plotted the ground truth as a red line. If you go back to the path of the diffusion, there's a state change about 1/3 into the run and 2/3 into the run. And we recovered those. Well, we have a peak into density close to those times, but there is also quite a lot of posterior mass or jump times in between. So this is actually a posterior where the jump times are not very well identified. And so essentially, the consequence of that is that the parameter posterior is, the parameters themselves are going to be quite ill-identified a posteriori. Anything else I could say about this output? Right, and so this is a setting really in which that methodology doesn't work quite as well as in the ordinary diffusion case, because if we go back to that bound on the path integrand, that is tight and small for small steps, theta dagger minus theta. But these steps optimally are going to be small if the posterior, if theta is well identified a posteriori, which is not the case here. So here we have to use a very large step to traverse the entire posterior. And so the path integrand is going to be fairly large, which as a consequence leads to fairly small coin probabilities both in the numerator and the denominator. And again, as a consequence, the two-coin algorithm tends to take a long time to terminate. So this setting isn't entirely convenient for the methodologies that we have developed. But as you can see, if you run the algorithm for long enough, then you come fairly close to at least recovering that invariance, that posterior invariance that we know must exist. Conversely, if you think of an entirely different trajectory of that diffusion, where mean reversion is much faster. So think of having that state change in y, and then reverting to the low stationary mean much more quickly, and vice versa. There, your regime process y would be better identified a posteriori, and as a consequence, so would be the parameters. Conversely, you would have a very strong drift close to those change points in y. And having a very large drift also tends to slow down the two-coin algorithm, because a large drift corresponds to large values of theta, and so either situation isn't entirely ideal for us. And none of those would arise in the ordinary diffusion case. And still, I think that we can come up with satisfactory answers by running the algorithm a little longer. And so where does that leave us? In order of importance, we are finishing the algorithm for more general forms of the instantaneous volatility sigma. The main issue here is that x becomes discontinuous if you allow sigma to depend on y. This was entirely simulated data from the correct model. And typically, well, your model is going to be misspecified for any real data set. And this will tend to slow down your algorithm. So this is something that we're still working on. We want to benchmark the algorithm based on the Bernoulli factory against pseudo-marginal implementation. And we'd also like to provide some theory of which rate of posterior contraction we need to keep the parameter, the optimal parameter step small, and give us a scalable algorithm. Finally, we're also interested in looking into map estimation for y, which this algorithm doesn't give you. It gives you marginal posterior expectations for the state of y at each point in time, but it doesn't give you the map trajectory. And it might be interesting to try this algorithm out for a hidden Markov model with more than two states. And another question that is quite important, but probably utterly intractable, is the optimal scaling of that algorithm. So that would be the the typical size of that difference between theta dagger and theta, where for the ordinary Barker algorithm, the optimal acceptance probability of the proposal is, I think, 0.17, which is a bit smaller than for the Metropolis Hastings, where it's 0.234. But a larger step actually is going to slow down the two-point algorithm. So really here we have a trade-off between efficiency in the two-point algorithm and draw MCMC efficiency, just in terms of the dependence of theta any two times in the Markov chain. And so 0.17 really here is the lower bound on the optimal acceptance probability. As an example, in this run here, I used an optimal acceptance probability of 1/3, but I don't actually know for a fact that this is anywhere close to optimal. And there is going to be a preprint on this soon, where we go into all of the details that I just have to gloss over here, because I'm already running out of time. So that should appear soon. And I hope that, if nothing else, I managed to whet your appetite a little and to keep you on the lookout for that preprint.